Imagine waking up to the news that an asteroid is on a collision course with Earth, set to impact within hours. The potential consequences are catastrophic. An asteroid striking our planet could unleash energy equivalent to millions of nuclear bombs, leading to widespread destruction, fires, and tsunamis. Urban areas could be obliterated, and entire ecosystems could be devastated. The urgency of the situation cannot be overstated. Every second counts in assessing the threat and mobilizing a response. The impact could result in significant loss of life, disrupt global economies, and lead to long-term environmental changes. Governments and scientists would scramble to implement emergency protocols, but the window for action would be alarmingly narrow. This scenario serves as a stark reminder of our vulnerability to cosmic events and the importance of being prepared for such an unprecedented crisis. Understanding the risks and potential responses is crucial as we navigate this existential threat to humanity. Throughout Earth's history, asteroid impacts have played a significant role in shaping the planet and its life forms. One of the most notable events occurred approximately 66 million years ago, when a massive asteroid, estimated to be around 10 kilometers in diameter, struck the Yucatan Peninsula in present-day Mexico. This catastrophic event is widely believed to have triggered the mass extinction of the dinosaurs, along with 75% of all species on Earth. The impact released an enormous amount of energy, equivalent to billions of atomic bombs, resulting in wildfires, tsunamis, and a nuclear winter effect that drastically altered the climate. Prior to this, other notable impacts, such as the Tunguska event in 1908, demonstrated the potential for destruction from smaller asteroids. These historical events remind us of the vulnerability of our planet and the importance of understanding the risks posed by near-Earth objects, as they can lead to profound and lasting changes in Earth's biosphere. Detecting asteroids, especially those that could potentially collide with Earth, is a critical task for astronomers. Various technologies and methods are employed to track near-Earth objects. One of the primary methods is the use of ground-based telescopes equipped with advanced imaging technology. These telescopes can scan the sky for moving objects, identifying asteroids based on their motion against the background of stars. Additionally, space-based observatories, such as the Near-Earth Object Wide Field Infrared Survey Explorer, utilize infrared sensors to detect asteroids that might be too dim to observe from the ground. Another significant method involves radar observations, which bounce radio waves off asteroids to determine their distance, speed, and trajectory. Astronomers also rely on computer algorithms to analyze data and predict the future paths of these objects. Collaborative efforts among international space agencies enhance detection capabilities, ensuring that even smaller asteroids are monitored. This comprehensive approach is essential for assessing potential threats and preparing for any necessary defensive actions. The size and speed of an asteroid are critical factors that determine the extent of damage it could inflict upon impact. A small asteroid, measuring just a few meters across, may disintegrate in the atmosphere, causing minimal harm. However, larger asteroids, those exceeding 100 meters, possess the potential to unleash catastrophic consequences. For instance, an asteroid traveling at a speed of approximately 20 kilometers per second can generate an explosion equivalent to millions of tons of TNT upon impact. This immense energy release can lead to widespread destruction, including shock waves, fires, and tsunamis, depending on the impact location. The diameter of the asteroid also influences the size of the impact crater and the area affected. A larger asteroid not only causes immediate devastation, but can also have long-term environmental effects, such as climate change due to dust and debris blocking sunlight. Understanding these dynamics is crucial for assessing the potential threat and developing effective mitigation strategies to protect our planet. As the threat of an asteroid impact looms, various defense strategies have been proposed to mitigate this risk. One of the most discussed methods is deflection, which involves altering an asteroid's trajectory to prevent a collision with Earth. This can be achieved through kinetic impactors, where spacecraft collide with the asteroid, imparting enough force to change its path. Another technique is disruption, which aims to break the asteroid into smaller, less dangerous pieces. This can be accomplished using nuclear devices detonated near the asteroid, creating a shockwave that alters its course. Additionally, the gravity tractor method offers a more gradual approach, where a spacecraft uses its gravitational pull to gently nudge the asteroid over time. Each of these strategies presents unique challenges and benefits, and ongoing research is crucial to determine their effectiveness. By investing in these innovative techniques, we can enhance our preparedness for potential asteroid threats and safeguard our planet. The kinetic impactor method is a proactive strategy designed to prevent asteroid collisions with Earth. This technique involves sending a spacecraft to collide with an asteroid at high speed, effectively changing its trajectory. The fundamental principle is straightforward. By impacting the asteroid, the spacecraft transfers momentum to it, altering its path over time. NASA's Double Asteroid Redirection Test mission, which launched in November 2021, serves as a prime example of this method. The spacecraft was directed to strike a small moonlet orbiting a larger asteroid, demonstrating the potential effectiveness of this approach. The success of the kinetic impactor relies on precise calculations, including the asteroid's size, composition, and trajectory. By carefully timing the impact, scientists can ensure that even a small change in the asteroid's path can lead to significant alterations in its future trajectory, potentially preventing catastrophic impacts on Earth. This method represents a promising avenue in planetary defense strategies. The nuclear option presents a dramatic yet potentially effective strategy for altering an asteroid's path. By detonating a nuclear device near the asteroid, the explosion can generate a powerful shockwave, which may push the asteroid off its collision course with Earth. This method relies on the principle of imparting momentum to the asteroid, allowing it to gradually change its trajectory. The key advantage of this approach is its ability to affect larger asteroids that may not be easily deflected using conventional methods. However, careful calculations are crucial to ensure that the nuclear blast occurs at the right distance and angle to achieve the desired effect, without fragmenting the asteroid into smaller, potentially hazardous pieces. While the nuclear option could be a game-changer in planetary defense, it raises significant concerns regarding safety, international treaties, and the potential for unintended consequences. Therefore, thorough planning and international cooperation would be essential to implement this strategy responsibly. The gravity tractor method is a fascinating approach to asteroid deflection that utilizes the gravitational pull of a spacecraft to gradually alter an asteroid's orbit. This technique involves positioning a spacecraft near the asteroid without making physical contact. The spacecraft's gravitational force, although weak, can create a subtle but continuous effect on the asteroid over time. By maintaining a precise distance, the spacecraft can influence the asteroid's trajectory, effectively nudging it away from a potential collision course with Earth. One of the significant advantages of the gravity tractor method is its ability to provide a gentle and controlled change in the asteroid's path, minimizing the risk of fragmentation that could occur with more aggressive methods. This approach requires careful planning and long-term commitment, as the process can take years to achieve significant results. As we explore this innovative strategy, it becomes clear that the gravity tractor method represents a promising avenue for planetary defense against potential asteroid threats. In the face of potential asteroid threats, international collaboration is crucial. No single nation possesses all the resources or expertise needed to effectively detect and defend against these celestial bodies. Global efforts bring together diverse technologies, knowledge, and funding to create a comprehensive defense strategy. Organizations such as the United Nations Office for Outer Space Affairs are pivotal in fostering cooperation among countries, ensuring that data on near-Earth objects is shared promptly and efficiently. Collaborative initiatives like the Asteroid Impact and Deflection Assessment Mission exemplify how countries can unite their efforts for a common goal. By pooling resources, nations can enhance their detection capabilities and develop more effective defense strategies. Furthermore, a unified approach allows for the establishment of international protocols for responding to potential threats. This collective commitment not only strengthens our planetary defense, but also promotes peaceful cooperation in space exploration, ultimately ensuring a safer future for all humanity. Space agencies like NASA and the European Space Agency, or ESA, play a crucial role in developing asteroid defense programs and technologies. These organizations are at the forefront of research, innovation, and international collaboration aimed at protecting Earth from potential asteroid impacts. NASA's Near-Earth Object Program focuses on identifying and tracking asteroids, providing essential data for risk assessment. ESA complements these efforts with its Hera mission, which aims to study binary asteroid systems and test deflection techniques. Both agencies work together on initiatives like the AIDA project, which seeks to understand how to alter an asteroid's trajectory effectively. Their combined expertise is vital for developing technologies such as kinetic impactors and gravity tractors. Furthermore, these agencies engage with global partners to ensure a coordinated response to asteroid threats. By advancing our understanding and capabilities, NASA and ESA significantly enhance our preparedness for potential asteroid encounters, underscoring the importance of their ongoing efforts in planetary defense. To effectively prepare society for potential asteroid threats, public awareness and education campaigns are essential. These initiatives aim to inform citizens about the risks posed by asteroids and the importance of readiness. Engaging content can include workshops, informative videos, and interactive social media campaigns that explain asteroid detection and defense strategies. Schools and community organizations can play a pivotal role by integrating space science into their curricula, fostering a culture of curiosity and preparedness among young people. Moreover, collaboration with media outlets can amplify these messages, ensuring that information reaches a broad audience. Public service announcements can highlight the significance of understanding response strategies, such as evacuation plans and emergency protocols. By increasing awareness, we can cultivate a society that is not only informed, but also proactive in supporting asteroid defense initiatives. Ultimately, a well-informed public can contribute to the collective efforts needed to safeguard our planet from potential asteroid impacts, emphasizing the necessity of ongoing education and engagement. The consideration of ethical implications surrounding the use of nuclear weapons in space is a complex and critical issue. While deploying nuclear devices may offer a potential solution to redirecting an asteroid, the risks involved cannot be overlooked. First, the detonation of a nuclear weapon in space could lead to unforeseen consequences, including the creation of space debris that might threaten satellites and other spacecraft. Furthermore, the moral dilemma arises from the potential for nuclear fallout, which could affect Earth's atmosphere and environment. International treaties, such as the Outer Space Treaty, prohibit the placement of nuclear weapons in space, raising questions about legality and accountability. The decision to use such weapons must weigh the immediate threat of an asteroid against the long-term risks of nuclear proliferation and environmental damage. Ultimately, a careful assessment of these ethical considerations is essential to ensure that humanity's response to asteroid threats is both effective and responsible. Implementing effective asteroid defense strategies presents several significant challenges. One of the primary obstacles is funding. Developing and deploying advanced technologies for asteroid detection and deflection requires substantial financial investment, which often competes with other pressing national and global priorities. This leads to inconsistent funding levels across different space agencies and countries. Additionally, technology limitations pose a major hurdle. Current methods for tracking and altering an asteroid's trajectory are still in their infancy. Many proposed techniques, such as kinetic impactors or gravity tractors, require further research and testing to ensure their effectiveness and safety. Moreover, political will plays a crucial role in the advancement of these strategies. International cooperation is essential, yet varying national interests and priorities can hinder collaborative efforts. Without a unified approach and commitment from governments worldwide, the progress in asteroid defense may remain slow and fragmented, leaving Earth vulnerable to potential impacts. As we look to the future, advancements in asteroid detection and defense technologies could significantly enhance our preparedness against potential threats. One promising area is the development of more sophisticated telescopes equipped with artificial intelligence, allowing for real-time tracking and analysis of near-Earth objects. These systems could identify potential hazards much earlier than current methods, giving us more time to react. Additionally, advancements in propulsion technologies could lead to faster spacecraft capable of intercepting asteroids. Concepts like solar sails or ion propulsion systems could enable missions to reach asteroids in shorter time frames, improving our ability to employ deflection strategies. Moreover, international collaboration on a global scale could lead to shared databases and resources, enhancing our collective knowledge and response capabilities. The integration of machine learning algorithms in data analysis could also streamline detection efforts, making it easier to predict asteroid trajectories. Together, these advancements could create a robust framework for planetary defense, ensuring a safer future for all. In conclusion, the threat of asteroids impacting Earth is a pressing concern that demands our immediate attention. Proactive measures, such as developing advanced detection systems and implementing effective defense strategies, are crucial in safeguarding our planet. Global cooperation plays an essential role in this endeavor, as no single nation can tackle the challenge of asteroid threats alone. By sharing knowledge, resources, and technology, countries can enhance their collective ability to detect and respond to potential impacts. Ongoing research is vital to improve our understanding of asteroids and refine our defense techniques. Furthermore, public awareness and education can empower individuals to support these initiatives. Vigilance is key. We must remain alert and prepared for any potential threats from space. Together, through collaboration and innovation, we can ensure a safer future for generations to come. The time to act is now, as every moment counts in our quest to protect Earth from these celestial dangers.